Here's to the second segment of the third lecture for the online series of lectures through the course of Dynamical Systems. In the previous segment, towards the end of it, we stated and proved a result saying that the domain of the flow map is an open set of R cross U. So in this segment, we'll start with the definition of flow map of a vector field. So let's get started with the definition of flow map of a vector field. For each point t comma p in the domain D, let u sub p from j sub p to big U denote the unique solution to the IVP 8, which was, let me write down the IVP 8 here, which is dx over dt is equal to f of x for an autonomous system, and x at 0 is equal to p. So this is IVP 8, and this guy is taken to be the unique solution of this IVP, defined on a maximal interval of existence j sub p. Now we put, as before, theta of t comma p is equal to u sub p of t for all t comma p in the domain D, which is equation number 9. Okay, this map theta, the map theta from calligraphic D to big U is called the flow map. Flow map of the vector field, of the underlying vector field F. Equivalently, we say that theta is called the flow map. Theta is called the flow map of the differential equation dx over dt is equal to f of x. This is equation number 10. Okay, now we discuss some properties of the flow map. Some properties of flow map along with proofs. Properties of flow map. Which we state by means of a proposition. Proposition 2. This states that the flow map theta from the domain calligraphic D to big U is continuous on D. On calligraphic D. Okay, here goes the proof. Let T1 comma P1 belongs to the domain calligraphic D. So we now prove that, which is equivalent to proving that it's continuous, which is equivalent to proving that theta is continuous. So the limit of this expression, theta of t comma p minus theta of t1 comma p1, okay? So I take the norm of this expression and take the limit as the ordered pair t comma p approaches the ordered pair t1 comma p1, and if theta is continuous, it has to be 0. This is equation number 11. This is what we want to prove. Okay, now let u sub p1 from the maximal interval of existence j sub p1 to big U be the unique solution of the following IVP. Unique solution of the IVP dx over dt is equal to f of x, and x at 0 is equal to p1. Okay, this is equation number 12. And this solution is defined over a maximal interval of existence jp1. Now since t1 comma p1 is in the domain calligraphic D of the flow map, one must have t1 belonging to j sub p1. Okay, it follows from the definition of calligraphic D. Now I assume that t1 is positive as before. Assume t1 to be positive. The case t1 negative can be dealt in a similar way. Then u sub p1 is defined on this closed interval 0 comma t1. Okay. Now consequently, by extensibility lemma, up1 u sub p1 is also defined on 0 comma t1 plus delta 1 for some positive delta 1. Okay. So follow the argument we presented while proving that this domain D is an open subset of R cross U. We use similar arguments there in that proof. So follow the arguments there. Okay. Now, by the continuous dependence on initial conditions theorem, one can proceed to show that so by using, let me write it here, by using continuous dependence on initial conditions theorem, there exists a positive number R1 such that whenever the norm of P minus P1 is less than R1, one has the solution of the IVP dx over dt is equal to f of x of 0 is equal to p, to be defined on 0 comma t1 plus delta 1. It follows from continuous dependence on initial conditions theorem. Okay, good. So far so good. Let me erase this part. Okay, now remember equation 36 of lecture 2? So I want you to go back to equation number 36 of lecture 2 and see that the calculation there which led to the following equation will also lead us to the following, which is as follows. The norm of the difference of these two vectors up of t minus u sub p1 of t is less than or equal to the norm of p minus p1 times e to the kt for t belonging to this closed interval t1 plus delta 1. Okay, so you can easily see how we can arrive here using equation 36 of lecture 2 by taking t0 equal to 0 in 36 of lecture 2. Okay, so take the lecture note there and have a look at equation number 36 and substitute t0 to be 0 and you will get it. Okay, for this case. Okay, because it was like t0 in that case and we substitute t0, the left endpoint of the closed interval we choose to be 0 in this case, and that's why we have this expression. Okay, good. This is our equation number 14. And this holds for some constant k, provided or as long as we choose p such that the norm of the difference of these two vectors p minus p1 being less than r1. Okay, good. Thus, if the norm of p minus p1 is less than r1, we obtain from 14 that the norm of upt minus u sub p1 t is less than or equal to the norm of p minus p1 times e to the k times t1 plus delta 1, which is the maximum possible value of t. I'm just substituting the maximum possible value of t here to get here for all t in this interval, because t can take values here, and I can see that this guy is bounded by this number, and which is the maximum possible number if I choose t plus delta 1 to be the value of t. Okay, good. This is our equation number 15. Okay, I need space Okay, this is 15. Now for the absolute value of t minus t1 being less than delta 1, and whenever we have the norm of p minus p1 to be less than r1, one has the following. The norm of the difference of these two vectors, theta t comma p minus theta t1 comma p1. So we know, we already know that theta t comma p is nothing but u sub p of t, and theta t1 comma p1 is u sub p1 of t1. Okay, now I can rewrite it as u sub pt minus u sub p1 t plus u sub p1 t minus u sub p1 t1. Okay, and by triangle inequality I can set it to be equal, less than or equal to the norm of u sub pt minus u sub p1 t plus the norm of u p1 t minus u p1 t1. This follows from triangle inequality by using triangle inequality. Okay, this is our equation number 16. Okay, now using 15 and 16 together, one obtains, using 15 and 16 together, one obtains the norm of the difference of the two vectors theta t comma p and theta t1 comma p1 is less than or equal to C1 times the norm of p minus p1 plus this guy. Okay, the norm of u p1 of t minus u p1 of t1. Okay, well here so this was 15. You see that I have so the first summand here is less than or equal to this expression. So that's what we are writing. We just chosen that C1 to be equal to this exponential factor. So where this holds for t minus t1, the normal, so the absolute value of t minus t1 is less than delta 1, and the norm of p minus p1 is less than r1, where this c1, this constant, is taken to be e to the k t1 plus delta 1. Okay, so this is our equation number 17. Okay, now I can erase this part. Okay, good. Now you see that since u sub p1 is a continuous function, since u sub p1 from j sub p1 to big U is a continuous function, one must have limit as t1 approaches t1, up1 of t is nothing but up1 of t1. Okay, using that fact, okay, we see that this guy goes to 0 as t approaches t1, and which leads to the following fact: limit of t comma p approaching t1 comma p1, we must have this guy to be less than or equal to 0, which means that it has to be 0 since it's a positive number. The norm of theta t comma p minus theta of t1 p1 is equal to 0, QED, which proves that the flow map theta from calligraphic D to big U is indeed a continuous function. Okay, now a remark following the statement of proposition 2. Let me write down the remark here. Okay, for the proof of proposition 2, of proposition 2, all that we required to assume is that f be locally Lipschitz continuous in X. We just required to satisfy that f is locally Lipschitz continuous in the second variable X. Well, not in the second variable, because f is taken to be, not explicitly dependent on t, so just f is continuous, f is locally Lipschitz continuous in X, okay, because f is just a function of X. It's not f is a function of t comma X. F does not depend explicitly on t in this situation, okay, because we are considering autonomous system, right? Right. Okay, so this is what we assumed to prove the result of proposition 2. But if we assume that if we put stronger condition on f, like f is a C1 vector field, we can prove a result much stronger than the statement of proposition 2. So if we assume that f1 is, if we assume that f is a C1 map, or f is a C1 vector field, then the flow map theta from calligraphic D to big U is also a C1 map, is a C1 map as well. Okay, so we have seen that if f is locally Lipschitz continuous in X, then this flow map is a continuous map. That's what we proved in proposition 2. But if we put stronger condition on f, like f is a C1 vector field, then this flow map turns into a C1 map as well. not just a continuous map. It means that d theta over dt and d theta over dxi for I from 1 to n are all continuous on calligraphic D. Okay. Good. Now we are going to define continuous dynamical systems. Now we are all set to define continuous dynamical systems. We have all the tools that we require to define a continuous dynamical system. Okay. Here goes the definition of continuous dynamical system. Before defining it, we need to discuss a few things like group action and axioms of group action and all that. Let me do it first. Okay, continuous dynamical systems. Our focus now is continuous dynamical systems. Okay, we saw earlier that for any C1 vector field f from u to r to the n, okay, like f of x, okay, where x belongs to u and f of x takes value in r to the n. It's a C1 vector field, okay, meaning that all these functions are continuous functions for I from 1 to n. Okay, and this guy f is defined on an open subset u of r to the n. Okay, if this is the case, if it's a C1 vector field, let me write it for you. If f from u to r to the n is a C1 vector field defined on an open set u of r to the n, there exists a corresponding flow map. This is what we have seen earlier in the remark of proposition 2. In the remark following proposition 2, corresponding flow map theta from calligraphic D, the domain of the flow map, to big U, that open set, defined on this flow domain, defined on a flow domain D contained in R cross U, which we also proved to be an open set of R cross U. Okay. Okay, so if F is a C1 vector field defined on this open set U of R to the n, there is a corresponding flow map theta from D to U, where D is an open subset of R cross U. Okay, this is what we have seen already. So in other words, for each vector P in this open set U, the function U sub P from J sub P to big U, defined by UP of T equal to theta of T comma P for all T in this maximal interval of existence JP, is the unique solution. This guy is the unique solution to the following IVP. dx over dt is equal to f of x, the underlying vector field, and x at 0 is equal to p. And this solution UP is defined, the unique solution to this IVP is defined on a maximal interval of existence J sub P. Okay. Okay. And we also saw that this flow map theta from calligraphy T to U is a C1 map, as long as this vector field F is a C1 vector field. Okay. This is what we have seen already. Okay, now notice the following things. First, note that theta 0 comma p is equal to p for all p in U. This is our equation number 19. It follows from the definition of theta. Remember that theta t comma p is equal to up of t, and we know that up of 0 is equal to p, which leads us to the fact that theta of 0 comma p is indeed equal to p. Okay, and we also see that theta t plus s comma p is equal to theta of t comma theta of s comma p. This is equation number 20. For all p in U, and you see that since we are writing this expression, it means that t plus s has to be in this maximal interval of existence, meaning J sub p. Since we are writing this, we are again writing this. So S is expected to be in J sub p as well, right? And we want T and S to be in R. Okay. And S comma T plus S, they both need to be in this maximal interval of existence, J sub p. Okay. So 19 and 20, they can be seen more closely in the following way. I want you to, consider these two equations and think of them a little more deeply. It's important to notice that we wrote down the differential, the IVP earlier as, this was dx over dt to be equal to f of x, and x at 0 was equal to p. This was IVP 18, right? And well, since u sub p solves this IVP, one must have u sub p at 0 must be equal to p, right? And we already know that theta t comma p is u sub p of t. Therefore, theta 0 comma p must be equal to up of 0 is equal to p. So this makes sense, right? Okay. On the other hand, notice that theta t plus s comma p is nothing but u sub p of t plus s, right? Well, this can be written down as theta t so this is the left hand side, okay? You take this equation and the left hand side can be written down like this, and the right hand side theta t comma theta s comma p can be written like this, okay, using this definition of theta. And so in particular, and they are the same, okay? In particular, theta t comma p can be written down as theta t comma u sub p of 0, right? Okay, which is nothing but u sub p of 0 plus t, which is u sub p of t. Okay, this way 20 also makes sense. Okay. So from the uniqueness of the solution of the IVP, it follows that they have to be equal. Okay. For the case in which the identity 20 holds true for all T(s) in R, the flow of F defines an action of the additive group R on the set U. Okay. So now comes the definition of the action of a group on a set. Okay. Okay, let me write it here. For the case in which the identity 20 what was the identity 20? The identity 20 was this: theta t plus s comma p is the same as theta t comma theta s comma p. Okay, this was identity 20. Holds true for all t comma s in R. The flow of this vector field F defines an action of the additive group R on the set U. Okay, it's the action of the group R on the set U. So I hope you are all familiar with the definition of a group. Okay, that it is endowed with a group multiplication rule, and with respect to that binary operation, it has to be closed, it has to be associative, there has to be an identity, and there has to be inverse for each group element. Then you call that set a group. Okay. So indeed, the set of the real numbers endowed with the addition, the binary operation of addition forms a group. So that additive group R has the action on this set U in the following sense. So now we are defining This is the definition of group action. Definition of group action: if G denotes a group and S a set, an action of G on S is the map phi from G cross S to S. Okay, satisfying the following axioms, which are group action axioms, satisfying phi of E comma S, where E is the identity element of this group G, has to be equal to S for all small s in big S. Big S is the underlying set. Here E is the identity element of G. Identity element of G. And further to that, we want phi of GH comma S to be the same as phi of G comma phi of H comma S. Okay, for all small s in big S, and these group elements G and H are two group elements of the group G. This is equation number 22, and this is equation number 21. Okay, so now in the context of the flow of a vector field F, so this is the general notion of a group action on a general set S. Okay, but in the context of the flow of a vector field that we are considering here, okay, so let me write it in the context of the flow of the vector field F, if theta t comma p is defined for all time, and p is a vector in the open set U, then in this case the group action phi of t comma p is nothing but theta of t comma p in terms of the flow map. Okay, for all t comma p in R cross U. Remember that here the domain is taken to be the whole real line. The calligraphic D is the whole real line in this case. So that the group action, the additive group R acts on the set U. Okay. And the group action axioms meaning 21 and 22 are satisfied by the underlying flow map with the underlying group G equal to R, the set of real numbers or the additive group of real numbers. The group operation the group operation being addition, being addition, and the set S in our case is the open set U in view of the equation 19 and 20. In view of equation 19 and 20. Let me write equation 19 and 20 for you here. Okay, which was theta 0 comma p is equal to p for all p in U, and the second equation was theta t plus s comma p is equal to theta t comma theta of s comma p. Okay, for all t and s in R. Okay, so compare these two equations with these two group action axioms, and you will see that in our case the underlying group is the additive group of real numbers and the set is the open set U of R to the n. Okay, good. Now, okay, now for the particular case, where the action of the set of real numbers R on U is defined by the flow map, of a C1 vector field on U, C1 vector field on U. The map t comma p to theta of t comma p is also C1. We have seen it earlier. Okay. So whenever the vector field F is a C1 vector field, this map is also a C1 map. Okay. Now we are all set to define continuous dynamical systems. So here goes the definition of continuous dynamical system. Definition of continuous dynamical systems. Okay, a continuous dynamical system on an open set U of R to the n is a C1 map theta from R cross U to U, which satisfies the following group axioms. The group action axioms, to be more precise. Should have written it as the group action axioms, not the group axioms. Is a C1 map theta from R cross U to U, which satisfies the group action axioms. Theta of 0 comma p is equal to p for all p in U. This is equation number 23. And we also want theta of t plus s comma p is equal to theta of t comma theta of s comma p. This is for all p in U and all t and s in R. Okay, they have to be satisfied. So a continuous dynamical system is just this map theta, satisfying these two properties of group actions. So thus a continuous dynamical system can be thought of as a C1 action. We want that action. Well, in the general context, the action was denoted by phi. In our case, where we are considering the flow of a vector field, a C1 vector field F, the flow map is of course a C1 map as well. So in that sense, it's a C1 action because the flow map is actually the action, right? So can be thought of as a C1 action of the group R comma plus, meaning that it's the additive group of real numbers on the open set U of R to the n. So everything is encoded in this function theta t comma p. It means that this map is a C1 map, right? And the action is of the set of the additive group of real numbers on the open set U of R to the n. And this map theta is the continuous dynamical system. Okay, so we'll stop here in this second segment. In the third segment, we will provide a few examples of dynamical systems and carry on our discussions on continuous dynamical systems. Thank you for attending this second segment.